Here's my short series on vector mechanics. First of all, we're going to look at an introduction to vectors, including what they are, a bit of arithmetic and notation, magnitude and direction, and what I consider to be the vector equation. There seems to only be one that we have to use, and we use it again and again and again in many different forms. We'll then look at some simple SUVAT problems, impulse force questions, then moving on to proving collisions, finding out when an object's travelling in a given direction, for example due east, and then finally looking at some more complicated expressions for the distance between two objects at a given time. Now, we're not going to have time to go through all of that in just a single video, so I've put links on the side here. If you're interested in any of the following, then please just follow the links on the side. We'll start off with the introduction then. The idea behind vectors is essentially the same as thinking about points on a graph. The unit vector, unsurprisingly, is 1 unit length, and we choose vectors that are orthogonal or perpendicular to each other, much like our x and y axis are on the graph. Typically, the vector I represents the horizontal, or in some problems the east direction, and the j vector represents the vertical or north direction, or y direction as we might be used to. We can then create any other direction out of multiples of these horizontal and vertical vectors. So here we've got a diagonal direction that's shown as 4i minus 2j. And because we can't actually write in bold, we indicate our vectors by underlining them to say that these are bold letters. How do we do arithmetic with vectors? Well, let's start off with a vector p, which we're going to say is minus I plus 2j, so it looks like this, and a vector q, which is 3i minus 2j, so it's going to look something like this. What would happen if I was to add two lots of p and the vector q? Well, here's one lot of p, here's another lot of p, and here's the vector q. This is what happens when I add them together. And we can see that what we're going to result with is a single vector that looks like this. And we can already guess that this is going to be I plus 2j. Now let's show that on the left hand side as well. I'm going to use column notation to write down my vectors. So as opposed to writing down p as minus I plus 2j, I'm going to write that as minus 1, 2 as a column vector. And then q becomes 3 minus 2. So if I want to look at doing two lots of p, I want to do two lots of minus 1, 2. And add to that 3, negative 2. Well, that gives me minus 2, 4, added with 3, negative 2. And this is where the column vectors really come into their own, because I can very easily collect like terms. So the I components are 1 and the j components are 2. All that's left for me to do at the end is then to reinterpret that in terms of i's and j's. So that's an I plus 2 j's, and notice how I'm underlining my i's and j's to indicate that they are vectors. The final thing to say about vectors is if we want to travel in the opposite direction, then we take the negative vector. So here we have the vector p, which was travelling like so. If I wanted to travel in the opposite direction, I would need the vector minus p. So here we have the vector p, and to travel in the opposite direction, I would need to take the vector minus p. The next thing that we want to talk about is magnitude and direction. So let's just pick any old vector. So here we've got minus 3i plus 9j. When we're talking about magnitude, we want to be thinking Pythagoras. If I draw this vector out, minus 3i plus 9j, so here's my minus 3 and here's my 9. If I want to know how long that vector is, if I want to know its distance, its magnitude, then unsurprisingly I've got a right-angled triangle because my unit vectors are orthogonal, and I need to do 3 squared plus 9 squared square rooted. Now you might be asking at this point, why am I not doing minus 3 squared? Well, when we're talking about distance, we know that we don't need to involve negatives, we just need to involve magnitude. We just need to involve absolute sizes. And this comes out to be 9.5 units of whatever it is that we're talking about. When we're interested in direction, we're talking about right-angled triangles, we're going to be thinking about trigonometry. So let's go back to our example. We could, for instance, find the angle in here and we'll call that theta. So we would want tan theta equals 9 over 3. And again, I'm talking magnitude here. I'm only interested in the size of things. So theta would be tan inverse of 3, which comes out to be 72 degrees. Now I have to indicate that in a very specific way, so I'm either going to say, oh, what's happening with my pen? There we go. I'm either going to say that that is a distance measured round from I, so I could have, here's the horizontal I vector, and I could talk about it as being the angle in here, and to find that I'd need to do 180 less the 72, which would tell me that the angle would be 108 degrees from the vector I. Alternatively, I could be thinking about a bearing, so here is my north, and measuring round clockwise, I'd have to go 270 degrees to get to this point, plus the extra 72 would give me a bearing of 342 degrees. So when we're talking about our answers as to exactly what direction we're travelling in, we need to either give information about that relative to a j, or relative to an I, or as a bearing. And we'll see this again in later questions. Finally, what I refer to as the vector equation. Let's say that we've got a velocity. We know that we're travelling at 5i plus 3j. Well, I could be doing that here, or I could be travelling at 5i plus 3j over here, or I could be travelling at 5i plus 3j over here. The difficulty is, without a fixed position, I wouldn't know where I was at any given time. So what I need to do is fix a location. We need to know where we're starting from, and in this case I'm going to say we're going to start from minus 2i plus 4j, so here is my rooted fixed position. If I then travel 5i plus 3j from this point, I will know exactly where I am at any given time. So to write this down as an equation, we say my position at any given time, r, I don't know why we use the letter r, we just do, is equal to the position I was where I started, which is r0, r at time 0, plus, well, where we're talking about constant velocity, we know that we could work out distance by simply multiplying our velocity by time. Again, my pen's gone funny, so let's get rid of that and draw in a nice T. We don't only have to do this for displacement, we could be talking about velocities, in which case the final velocity, or my velocity at any given time, will be the velocity at the start. Notice here that we use v0, we don't use u, plus my acceleration multiplied by time. And this is what I would refer to as the vector equation. Where we are at any given time is where we were to start with, plus some multiple of a variable times time. Finally, relative displacement. Let's say I've got a vector here, RB, and I've got a vector here, RA. If this is the point A, and this is the point B, and I want to know how to get from A to B, sort of goes back to the work that we've done earlier on notation. To go from A to B, I need to travel back along my vector RA, so I need minus RA, and then I need to add on to that the vector RB. Now that tells me a vector of how to get from A to B, and we may see this sometimes written down as A to B is equal to B minus A in a sort of sloppy notation way, but we understand that it means that we need to travel backwards along the vector A and positively along the vector B. If I want to find that as a distance, I need to find its magnitude, and to notate that I put two lines either side of my vector, and this just means find the magnitude of. And whenever we think magnitude with vectors, we think Pythagoras.